This video demonstrates our prototype AbstractsViewer system and how we can use its post-hoc explanations and multi-scale comparative design to improve text corpus exploration. First, an overview of our system. We can start by searching for papers that we are familiar with. For instance, here we're searching for serendip. Below is the corpus map, a 2D projection of all the documents in the dataset. Hovering over the squares tells us the number of papers in each square and the words that describe the region. Search results are displayed as green circles in this view. Selecting a document from this table will pop up the document view with detailed information about the selection. Search terms are highlighted in green in the document view. Two lists of the most similar 10 documents of the selection using different embeddings are shown below the abstract. We can also make another selection that will show up side by side with the current selection. Common words between the two documents will be highlighted to aid relevancy assessment. Common words that appear in more than 10% of the documents in the whole dataset are highlighted in dimmed yellow, while the rest of the common words are in bright yellow. The corpus map view shows where in the corpus the selections and their neighbors appear. To take a closer look, we can select a region to enable regional views. A user-defined region can either be a selected square or a swept rectangle. When a region is selected, the detailed scatterplot view, regional matrix view, and regional list view are enabled. The detailed view displays each document as a circle or a star. Yellow refers to documents in the left list, while pink refers to those in the right list. Selections appear as stars. If a document is a similar document to both selections, it will be half yellow and half pink. The regional matrix is a reorderable, salient word by documents matrix. The regional list is a reorderable list of documents in the selected region. The combination of regional matrix and list provides item-based and feature-based explanations. Example 1, where we explain interpretable models locally. The tasks we address are to identify relevant documents, specifically relevancy assessment. The features that we use are the neighborhood list, pairwise word salience, and dual selection. Here we're looking at serendip, and we're trying to find other papers which are similar to or relevant to serendip's topic of text exploration. We can compare two papers with our dual view here by looking at these highlighted words to help us assess relevancy. We can see many similar words shared between these two papers, and they're also very specific and relevant to text exploration. Continuing down the list, we can look at some other papers. And again we see another example where the highlighted words are both similar and relevant to text exploration. However, continuing down the list again, we can see the similar highlighted words are there, however, they're more generic and not as related to text exploration, indicating that although this paper might have some similarity, it's probably not very relevant to our task at hand, showing us how we can use the highlighted words to quickly assess relevancy for papers. Example 2, where we explain a region in global context. The tasks we perform are to identify relevant documents, specifically identify terms, and to identify global context. The abstract viewer features that we use are the regional matrix, regional list, and the item plus feature based explanations. We continue on from our previous example, where we had serendip selected as our original paper. In our document view, we can see our secondary selection is a paper that we're assessing for relevancy. Based on the highlighted words, we're uncertain of its relevancy, so we can move over to the corpus map to get some more insight. In the corpus map, we can see that the points associated with our right selected paper, the pink points, are scattered across the place, whereas the papers associated with our left selection, serendip, are crowded towards the right-hand side. To get a better view of things, we can go ahead and select that area of the corpus map. This pulls up a scatterplot view, giving us a bit more detail into that region.
However, we're still not sure of the content and context of these papers. That's where two new views come into play, the regional matrix and the regional list. The regional matrix helps give us an initial impression of the content of these papers in this region. Then the regional list provides us a bit more concrete context of these specific regional wards. The combination of these two views, the combination of item and feature-based explanations, helps users interpret a map region and locate relevant dots more effectively. Example 3, where we explain a region using an uninterpretable model. The tasks we perform are to identify global context, and the AbstractViewer features that we use are multiple ward metrics and reorderable regional matrix. In this example, we're going to be using AbstractViewer to find papers related to the topic of explanations. So we type in our keyword into our search field, and then we can navigate down. Specifically for this one, we're going to go ahead and change our embedding type to Spectre. Now, Spectre is not a directly interpretable embedding, so we're going to have to rely on AbstractViewer's post hoc explanations to gain some additional insight and information about the papers in our results. To do this, we can select a region of our corpus map. And now we can go ahead and look at the regional matrix to get a general sense of the topic of this area. From these wards, it looks like these papers have to do with machine learning. We can gain additional insights by using different sorting metrics. For example, we can sort by uniqueness, which shows us wards that appear primarily in this region instead of others. This gives us some more specific context and information about these papers. Looking at our wards, we can see that they give us some information about the topics, techniques, and models used in these machine learning papers. Thank you for watching.